Dr. Helmut Knozinger, who will be chairman for this morning's plenary lecture. Dr. Knozinger.
Well, thank you. It's a great pleasure for me to be here, and it's a special honor to have the opportunity to introduce to you the first plenary speaker at the Summer Catalysis Olympics here in beautiful Calgary. The first plenary talk will be given by Professor Helmut Knozinger, one of the big stars of the German catalysis team. Professor Knozinger has during all his professional life been associated with the University of Munich. After receiving a degree in physics and physical chemistry with Professor Schwarz in 1957, he joined the Department of Physical Chemistry, where he since 1980 has been a full professor. Professor Knozinger's research interests have especially been in the areas of surface chemistry and surface spectroscopy, and he is well known for his many pioneering applications of vibrational spectroscopy. The aim of much of his work has been to characterize supported oxide, sulfide, or metal catalyst systems used for example, CO hydrogenation and hydrotreatment. Professor Knozinger is the author of close to 200 scientific articles. He is the co-editor of the recent book on metal clusters in catalysis, and he has written several excellent and much quoted review articles. Among the honors Professor Knozinger has received, it could be mentioned that he was named the 1980 recipient of the Capella Lectureship from the North American Catalysis Society, and he is also on the editorial board of many of our catalysis journals and periodicals. Today, Professor Knozinger will talk to us about hydrodesulfurization catalysts, one of the fields to which he has made many significant contributions. This field continues to be one of the most important areas in catalysis, as many papers at this meeting are clear evidence of. Hydrodesulfurization and hydroprocessing are indeed also areas of great national importance here in Canada, and many important research and process developments have come out of the laboratory of our hosts. Thus, in all respects, it is a fitting topic to start our conference with. And with this, I'll give the word to Professor Knozinger, and we'll all look forward to hear his lecture entitled Genesis and Nature of Molybdenum-based Hydrodesulfurization Catalysts.
Typically, naphtha contains about 400 ppm of sulfur example, demonstrated here by the reaction network of didental silane. The dominant reaction pathway is the primary splitting of sulfur carbon bonds by phenolysis of sulfur carbon bonds, followed possibly by hydrogenation and CC bond splitting. Typical catalysts for these processes are the homo and hemo type catalysts, typically supported on alumina, and this is the class of catalysts on which I will concentrate today. In addition, the nickel tungsten type catalysts are also used for specialty application. Obviously, the technological importance of the class of processes with catalysts lies in the fact that one has to remove catalyst poisons, water compounds, or catalyst poisons, and low level catalysts, which are being used in subsequent processes such as reforming, and in addition, certainly, they have to be with respect to environmental protection. The economic potential of these processes can perhaps best be estimated by considering the catalyst consumption per year and its development over a couple of years. In 1983, catalyst consumption was 25,000 to 30,000 pounds, corresponding in those days to a value of $150 million US. In 1986, this catalyst consumption had increased to almost 45,000 pounds. Now, the quality of catalysts today has been pushed to very high standards. I believe that further progress, further improvement can possibly only be reached Well, I believe that further improvement of this class of catalysts can possibly only be achieved if we understand in more detail the functions of these catalysts on a molecular level. This, in the first place, means that we need to learn about the nature of active sites, and this is related to the nature of active phases in the catalyst material. Once knowing those active phases, we need to synthesize catalysts which contain these active phases in high dispersion and high concentration. Therefore, I think today I will talk to you about preparational aspects, catalyst precursors, and the fate of these precursors during activation of the catalyst. I actually feel that it is very appropriate to devote the first lecture on the to the genesis of the catalyst. Now, I plan to discuss with you today the preparation of catalyst precursors in their oxide state for unpromoted and promoted catalysts, and will then turn to the sulfidation of these materials. I will briefly discuss the location of promoter atoms in the sulfide catalyst, nature of coordination sites, and finally make a few comments on dihydrogen activation. Now, let me start by reminding you of a statement given by Mitchell, who said that the crucial precursor of active sulfide catalysts would be a polymeric surface molybdate with molybdenum 6+ in octahedral oxygen environment. Let us assume for the moment that this is true. We then have to investigate whether and how we can synthesize those surface polymolybdates on this approved surface. Typically, at least at the laboratory scale, these catalysts are being prepared in their oxide precursor state either by impregnation in aqueous molybdate solutions and subsequent heat treatment, or, and I will briefly mention this alternative route, we can also prepare the precursors by a process which is called polysolid wetting in physical mixtures of oxides. Now, if we impregnate as a fluid, namely alumina, it has to be brought in contact with aqueous solution, and this will lead to surface polarization according to these two equilibria. First, describing the associative absorption of protons from solution. Second, describing the dissociation of surface hydrogen groups. Now, depending on the pH of the solution, this will lead to positive or negative surface charge, particularly when the pH of the solution is in the acidic regime relative to the isoelectric point of the particular solid. First equilibrium will lead to positive surface polarization, a situation which obviously is favorable for anion absorption. In fact, the molybdenate species in aqueous solution are anions, so to have good absorption conditions, we have to take care of a pH in the acidic regime relative to the isoelectric point of support. We also have to consider the solution equilibria of the molybdenate solution, which are written down here, where in the acidic regime, a natural pH of 5.5, for example, the heptamolybdenate ion is the dominant species. The structure of this material is shown down here. This is a three-dimensional structure of 7 H-sharing molybdenum oxygen octahedron. If the pH is shifted to the basic regime, this decondenses and forms heterodysyl monomer species. Now, these considerations would predict that we have good absorption from solution of the molybdenate ion when the pH of the solution is in the acidic regime relative to the isoelectric point. And this has been shown experimentally. In this slide, the molybdenum oxide equilibrium absorption study is plotted against the final pH, and it clearly is seen that at high pH, the basic regime molybdenum oxide is very low. It then rises as we approach the isoelectric point 7 and reaches the plateau in the acidic regime. Steep rise here in the very acidic range is probably due to precipitation. In contrast, silica, which has an isoelectric point near 2, does not absorb molybdenum to a large extent due to the fact that its surface will be negatively charged in almost the entire pH regime. Now, the question which now arises is relative to the nature of the adsorbed molybdenate species. Is it the monomer or is it the heptamer? This is not a trivial question, even if we start with natural pH and the heptamer, because the anion absorption, anion exchange absorption, will liberate hydroxide irrespective of whether we absorb the monomer or the heptamer. In each case, we will liberate hydroxide groups, and the consequence of this ion exchange absorption and liberation of hydroxide groups would be possibly an increase of the pH solution in the pore system of the support, which can lead to a shift of the molybdenate equilibrium to the left with decondensation of the heptamer, and in addition, the increased pH solution will reduce the molybdenum oxide. Now, it's very difficult to control these phenomena because most of the spectroscopic techniques we have applied to study these phenomena are not easily discriminating between molybdenate species in the solution at the pores and in the adsorbed state. Today, I would like to draw your attention to one, let's say, unconventional technique in catalysis research, which is indeed able to differentiate between these the adsorbed state and the solution. This technique is called time differential perturbed angular correlation, and has the acronym TDAC. I cannot go into detail, I will only try to briefly give you a flavor of the physics behind this technique, in particular for the case of molybdenum. We start out in tritium-98, which is transformed by neutron capture into molybdenum-99, which then emits an electron and leads to an excited nuclear state of the Ixum-99. This is our Ixum probe. On this, the Ixum-99 will then de-excite by emission of 2 gamma quanta in succession through an intermediate state, nuclear spin by far and the final point time. Now, in this experiment, one measures the angular correlation between the emission direction of these two gamma quanta in a situation where we have spherical symmetry around the probe atom in the intermediate state. This angular correlation will be unperturbed. However, if the environment of the intermediate state is non-spherical, we will have quadrupole interactions between the quadrupole moment of the atom and the electric field gradient, which is produced by the extranuclear charges at the position of the nuclear atom. This will lead to modulation of the angular correlation of the emission directions of these two gamma quanta, and this modulation is typically expressed as a perturbation function plotted to spectra as anisotropy as a function of time. I will just show you in this overloaded slide a few results to just try to convince you that we can differentiate the mean variance motivated species by this technique. On the left-hand side, we have the direct angular correlation spectra for the monomer in the top spectrum and heptamer in the lower spectrum. You clearly see that the features are entirely different, and this can be used as figures for the monomer and the heptamer in the same way and fully transformed as they reflected. Now on the right-hand side, you see the spectra of two wet capsules, which were both impregnated at pH 5.5, the natural pH, but at different loading. You see, although not identical, but this feature resembles the one for the monomer when we have low loading, whereas the one at high loading almost corresponds to the monolayer capacity of this particular capsule. The feature is very similar to that of the heptamer. Now, these studies can be done as a function of temperature, and the temperature dependence of the spectra actually permits the distinction between species in the solution and in the absolute state. The conclusion of such experiment is that under conditions where we prepare catalysts near monolayer coverage, the adsorbed species is preferentially the heptamer. Now, I must admit, perhaps, that this very brief discussion of this relatively complex technique may not have convinced you. But I think I can convince you by the next slide, if you would like to dim the lights a bit. We can even make visible the absorption of the heptamer. And this is due to the fact that neutron irradiation leads to the formation of color centers, intramolecular color centers in the heptamer. This leads to deep blue solutions. As soon as we put a drop of phase in this solution, it immediately loses color due to the fact that now the equilibrium is shifted to the monomer, and we destroy the color center. On the other hand, if we use this deep blue solution and put alumina in it, immediately the deep blue sediment appears, which is alumina with the adsorbed heptamer still containing the color centers in it, and the solution, supernatant solution, color. So I think this simple experiment really demonstrates that the heptamer is being adsorbed under these conditions intact on the surface. Now, the angular correlation spectroscopy is a quantitative technique, and we can calculate and determine, first of all, the degree of absorption for various catalyst preparations and the ratio of heptamer to monomer. Let us concentrate on the monolayer type catalyst, 12% weight molybdenum dioxide. The absorption is almost 100%, and the heptamer to monomer ratio is actually over 4, which corresponds to about 80 to 90% of all molybdenum being absorbed in the form of the heptamer. Now then, in conclusion, we find that in preparation or impregnation of aqueous solution at low slide, the ion scattering intensity ratios from molybdenum to aluminum are plotted in the concept for a calcined catalyst and monolayer loading versus the sputtering time. As you know, ion scattering is monolayer sensitive, and we would expect a initial ratio of infinity if we really had formed an entire monolayer on the surface covering all the alumina surface. Now we have a high ratio, but it does not tend towards infinity, indicating that these materials are in fact highly dispersed, but they leave uncovered alumina surface exposed. So the conclusion then may be that we do form perhaps three-dimensional MOX or Y island, and uncovered aluminum surface is still exposed. What is the structure of these MOX or Y islands? This can be solved by Brown spectroscopy, and in this slide I compare the solution spectra of the heptamer and the monomer with a typical spectrum of a catalyst recorded on alumina. Now, if you compare those spectra, you will come to the conclusion that all the features characteristic of the heptameric species appear in the surface spectrum. Lines are being drawn indicating distortion of the surface species due to anchoring to the surface, and this anchoring most probably occurs through the formation of molybdenum oxygen aluminum bonds during the calcination. These vibrations characteristic of these bridges typically should occur in the 800 to 900 wave number regime and are indicated by this broad shooter, which is very characteristic for the spectra of catalyst calcination. So the conclusion then would be that in the calcined catalyst, referential species would be heptamers, probably linked to the catalyst surface, to the support surface by molybdenum oxygen aluminum linkages. They would probably bear some protons for charge balance. Now these conclusions have been supported by UV visible spectroscopy and again by angular correlation spectroscopy, which again tells us the quantitative distribution. And from angular correlation we can conclude that the heptamer is in fact present to 80 to 90% of the total molybdenum, the remainder being monomeric species. Now if we do form these molybdenum oxygen aluminum linkages, we would expect that surface hydroxyl groups of the alumina would be removed. And this is in fact the case. Up here, formally I have written down the transformation of the electrostatically adsorbed heptamer with ammonium ions for charge balance, which will then be transformed into an anchored species still containing 7 molybdenum atoms with possibly protons for charge balance. And in the spectra down here, you see the typical OH region of alumina in the absence of any molybdenum, and then two spectra with increasing molybdenum content. You clearly see that the intensities will go down, and particularly that the high frequency hydroxyls are being removed, and those are the ones which correspond to basic, easily interchangeable hydroxyls. At higher loadings goes the monolayer coverage. We get only one probe band centered at around about 650 wave numbers, which probably contain contributions from remaining aluminium hydroxyl groups and hydroxyl groups being connected with molybdenum, and those may be Brent acidic, as has been indicated by periodic absorption. Now, the conclusion then regarding the structure of molybdenum species in calcined catalysts would be that the 80 to 90% of the total molybdenum anchored to the alumina surface by molybdenum oxygen aluminum linkages with structures similar to the heptamer known for solutions. These are probably bonded to the surface in small islands, which may contain 7 molybdenum atoms, and patches of uncovered alumina still exposed. Now, I will turn to the second approach to these surface species, and this is solid-solid red. In these experiments, mixtures of oxides with fumed oxide and alumina are being heat-treated, and under proper conditions, molybdenum trioxide will spread over the alumina surface. This can be followed again by ion scattering spectroscopy. We get a plot of molybdenum to aluminum ratio versus processes will occur if during the spreading process surface free energy change is negative. Now I should mention that this process of spreading occurs irrespective of the presence of water vapor or absence of water vapor during the process treatment. However, water vapor is essential for certain chemical transformation. We can transform molybdenum trioxide into a certain native heptamolybdate when water is present in the system, and this is clearly demonstrated again by Raman spectroscopy, the lower spectrum being characteristic of a calcine mixture in the absence of water, and the series of sharp lines is very characteristic of molybdenum trioxide. No structural changes as regards vibrational spectroscopy, however, still spreading over the surface. If we have water in the system during calcination, then the spectrum dramatically changes, and comparison of this spectrum, the solution spectra of the heptamolybdate indicates that we have entirely transformed the molybdenum trioxide into a surface feature heptamolybdate. It is interesting to know that, I should just explain the chemistry behind this transformation. It's almost sure that molybdenum trioxide in solid state may react with water to form an oxyhydroxide, which then can react with a surface hydroxyl group to form a surface native monomer species. And as the local concentration of these monomers increases, they may condense and form the heptameric species. In fact, Raman spectroscopy has permitted to detect those monomers as intermediates in the whole process. It's interesting to look into the activity for thiophene hydrodesulfurization as mild conditions for these preparations. Now the top curve is characteristic of a material prepared in the presence of water, and the lower curve is the one obtained for a material prepared in the absence of water. Remember, the precursor here is the heptamer, the precursor here is molybdenum trioxide. You clearly see that the activity is significantly lower for the material prepared under dry conditions. This again we support the suggestion of Fischl that the heptamer or the polymer is an important precursor for the applied catalyst. In addition, in this slide, we see the comparison of activity for the materials prepared by solid-solid wetting in the presence of water and the conventional impregnated materials with the same molybdenum loading. The activities and decaying activity this time on screen is absolutely identical. So the conclusion then is that spreading solid-solid mixtures can be considered as an alternative route towards the preparation of the precursor for which this catalyst is not promoted. Now, the final conclusion then, coming back to Fischl's prediction, is that we can in fact synthesize into the predicted precursor. Now, actual catalysts are promoted, typically promoted by coal and nickel. In a very brief survey, I would like to mention here the compounds which we can principally expect, and I can only dwell on typical compositions given down here as the ratio of the promoter concentration over promoter plus molybdenum concentration of 0.3, which would correspond to a promoter to molybdenum ratio of between 0.4 to 0.5. These are the typical compositions. We can expect all these compounds in principle. I have put in frame those which are actually being found in typical catalysts surface polymolybdate in interaction with the promoter atom, surface cobalt or surface nickel aluminate. Now in the case of cobalt, the tendency to form aluminates is much lower than that for nickel, and therefore under certain conditions we may also find some cobalt oxide here. Now the structure of these promoted materials seems to be very similar regarding the molybdenum part as in the unpromoted system. This is shown by X-ups. The feature here is almost entirely identical to the feature which one obtained for an unpromoted catalyst, indicating very critical aspect because those promoted acids penetrating even the important matrix are being lost for promotion. And therefore the control of the distribution of promoted acids between surface and health is of critical importance. I'd like to show you one example where we have prepared two types of nickel polycatalyst. The NEMO type is one where the molybdenum has been impregnated first, oxide, and nickel has been impregnated in the second step, whereas for the MOMI, the impregnation sequence was just nickel. Ion scattering spectroscopy now plotted as nickel to molybdenum density ratio versus bombardment time indicates that the nickel to molybdenum ratio for the NEMO type catalyst is much higher than that for the MOMI type catalyst, indicating that for the case where nickel is impregnated first, we do in fact more significant surface nickel aluminate, and nickel is no longer present in the surface for promotion. And this has significant influence on the catalytic activity in the sense that HDS activity was much higher for the NEMO than for the MOMI catalyst. Now these results can also lead to some information regarding the interaction between nickel and molybdenum, but this perhaps can be better demonstrated by the adsorption of nitric oxide. And the next slide demonstrates this for the cobalt polycatalyst. Both cobalt and molybdenum absorb nitric oxide in form of dinitrosyl species. At the bottom spectrum you see the characteristic feature for the dinitrosyl on molybdenum. The second spectrum is the dinitrosyl on the cobalt containing catalyst. The third spectrum is the physical mixture of these two. You see the molybdenum feature here and the unshifted doublet for the cobalt dinitrosyl. In contrast, when a cobalt monocatalyst is being considered, we see the molybdenum contributing here, and in addition again the doublet characteristic for dinitrosyl located on cobalt, but now there is a frequency shift to higher values, which has been interpreted as characteristic of a cobalt molybdenum interaction. Now at this point, we can perhaps draw a very oversimplified picture of the structures and distribution of elements in the oxide precursor state catalyst. The top picture is perhaps more relevant for the cobalt case, where some tetraethyl cobalt is penetrated into the bond, is lost for promotion. On the surface we do have molybdate polyanions, and there is octaethyl cobalt located close to the surface integration with the molybdate. The lower description may perhaps be more relevant for nickel-promoted materials, where we do have octaethyl and tetraethyl nickel in the aluminate matrix, and we do seem to have some bigger atoms located within the molybdate species or on top, indicating perhaps the formation of surface analogs of nickel tetrapolymolybdate. Now these materials, either molybdate species, including alumina, or in interaction with promoter atoms for promoted materials, are the precursors for sulfidation. Sulfidation has been studied, the process has been studied by temperature program sulfidation, and these experiments have demonstrated that an oxygen-sulfur exchange seems to precede the reduction of the molybdenum. Raman spectroscopic evidence was obtained for the fact that hydroxysulfides are being formed as intermediates in the sulfidation process, and evidence was also obtained by Raman spectroscopy for the formation of SH, disulfide bridges, and molybdenum oxygen bridges. Schematically, those intermediates have been depicted in this form, where the species contains 7 molybdenum atoms, because this means that it is directly formed in the unpromoted state from the hexamer in the oxide precursor state. Now the further phase during sulfidation has been studied by EXA in much feature. Up here, you see the characteristic exhaust features for a catalyst supplied under mild conditions. The MOS and molybdenum distances suggest that species which are similar to MOS2 are being formed. However, there are additional features in the regime where we expect the molybdenum oxygen distances. In comparison, you see here the exhaust features of the precursor of this particular catalyst to molybdenum oxygen. Here. Also, comparison of the exhaust features of the catalyst with the authentic features of MOS2 polycrystalline indicates that, first of all, the first coordination here, the relative intensity of the molybdenum distances are reversed, and furthermore, the higher coordination shells cannot be seen in the catalyst. This suggests that the MOS2 species are either very distorted or highly dispersed, containing only few molybdenum atoms in each part. Now, the perhaps best description of the sulfide catalyst or promotion catalyst is as following. Under mild sulfidation conditions, we seem to form highly dispersed MOS2. Evidence is given for the existence still of molybdenum oxygen aluminum plating here, probably stabilized behind dispersion. The slabs should be very small, the size is estimated to be below 3 nanometers. And this description, again, is in nice agreement with information from Raman, spectroscopy, and angular correlation figures. At this point, you can ask the question, how these MOS2 type slabs would be oriented relative to the supporting surface. And this can be tackled by electron microscopy, which is in the light beam. This is an electron micrograph of polyalumina sulfided under relatively mild conditions. And typically you see black lines in this micrograph. Standard as demonstrated by computation and through focus behavior of the micrograph, that these black lines should be formed from single layers of molybdenum solvents, which are oriented more or less parallel to the electron beam. Furthermore, using tilting experiment, Brett and Sanders came to the conclusion that these should be almost planar and stand vertical to the supporting surface. This has been done in the following way. You see slabs, lines which are almost parallel to the tilt axis, indicated by the white arrow, and you see lines which are almost vertical to the tilt axis, indicated by the black arrow. Now, on tilting, those lines which are vertical to the tilt axis do not change in contrast during tilting. On the other hand, the parallel lines appear and disappear on tilting. And it was suggested that this behavior on tilting is typical for two-dimensional slabs which are planar and should stand upright on the supported surface. Now, this view, in fact, has been nicely supported by model studies by Hagen and Dumezi, where they prepared planar alumina model supports, evaporated into trioxide onto and sulfided under various conditions. Under mild sulfidation conditions, they find edge-bonded MOS2 slabs which roughly stand upright on the support surface with a truncated 2, 1, 2, minus 1, minus 1, 0 line being anchored to the surface, and 1, 0, minus 1, 0 edges being preferentially exposed to the gas. Now, if the sulfidation conditions were more severe, then apparently the slabs are being detached from the surface, and they start to lie planar, parallel on the surface. They become basal bonded under more severe sulfidation conditions. Interestingly, Delaney had already suggested that MOS2 slabs after sulfidation at very high temperatures, corresponding to the temperatures in the model experiment, were also parallel to the observed. Now, promoting catalysts have been studied in the sulfidation process, has been studied by Eckert again. It was indicated that sulfidation of molybdenum seems to proceed through steps analogous to those in unpromoted material. Possibly the dispersion of the hemolysis levels is slightly higher in promoted material than in unpromoted, and most of the cobalt seems to be sulfide. Less power emission spectroscopy has indicated the working of 3 different types of cobalt. Cobalt in tetrahedral coordination into oxygen, which is apparently cobalt which is penetrated into the illuminated matrix and not be sulfided. Then cobalt CO9S8 in some cases can be detected, but it is only detected when the precursor material contains cobalt oxide. And there is a linear correlation between the concentration of cobalt oxide in the precursor and CO9S8 in sulfide catalyst. Finally, a new phase was detected. We'll discuss this in a minute. It was called the cobalt phase. And this is related to the cobalt octahedral coordination in interaction with the surface. So let's say, again, there is a linear correlation between the amount of cobalt octahedral in the oxide precursor and the cobalt in the cobalt phase. Now, at this point, we can summarize our picture of the sulfided catalyst. The nature of the sulfided catalyst apparently consists in hemolysis-like slabs in high dispersion, which seem to be directly formed from the surface epithelial species in the oxide precursor. After mild sulfidation conditions, these hemolysis slabs seem to be anchored to the support by molybdenum and aluminum linkages, and the slabs seem to be normal to the surface. When sulfidation conditions are unusually severe, high temperatures, 800 Kelvin, 500 Kelvin, the slabs seem to be detached from the support surface by splitting across bonds. They are then oriented parallel to the support with less support interaction, and the slab size is made of larger. The promoter atoms have been shown to be in the disorder phase, and evidence for molybdenum cobalt interaction, particularly for carbon-supported materials. At this point, we may ask ourselves what the location of the promoter atoms in these materials would be. Now, it is well known and has been verified by a number of nice small experiments, maybe using molybdenum sulfide monocrystals, that the laser lines of these materials are chemically almost inert, and chemical reactivity is located along the edges of the nucleus that the edge atoms are coordinated unsaturated. On the basis of these considerations of this kind, Ratnasamy and Sivasankar predicted that the promoter atoms should possibly decorate the edge plane of hemolysis slabs. Knozinger, in fact, have provided experimental evidence for the effect of decoration of hemolysis slabs, and they call these new phases homos or homos phases depending on the type of promoter, and they also show that these phases are relevant for the magnetic activity. Now, the segregation of cobalt onto the edge phases has been very nicely demonstrated by Gianelli in model experiment. On the left-hand side here, you see a big crystal of cobalt containing MOS2, giving you the steps exposing the edges, and then the Auger backing and the cobalt energy range was made of these materials. You really see that the cobalt is actually decorating those steps and edge planes. Also, it has been estimated that most of the cobalt can actually be accommodated in catalysts of typical compositions along the edges if one assumes slab sizes of about 3 nanometers and smaller, and one assumes one cobalt atom per molybdenum atom along the edges. Now this stoichiometry very nicely corresponds to the experimentally determined edge stoichiometry cobalt molybdenum of OC. Now, catalytic studies of thiophene hydrodesulfurization in conjunction with Nussbauer emission spectroscopy has led the toxic group to the description of two types of form spaces, namely type 1 and type 2. Type 1 phase is formed under mild, typical sulfidation conditions, whereas the type 2 phase results from severe sulfidation conditions at high sulfidation temperature. These two straight lines clearly indicate that the activity of the rate of hydrodesulfurization is linearly correlated with the number of cobalt atoms in the cobalt space, indicating that the catalytic activity should be associated with cobalt in the cobalt space. The second interesting result to be deduced from these data is that even in the absence of cobalt promotion, the type 2 phase provides higher activity by extrapolation to zero cobalt than the type 1 phase. Now this probably has to do with the fact that the pore interaction sensitively influences catalytic activity. Remember, the type 1 phase is prepared under mild sulfidation conditions, for which we have found small slabs being anchored to the support surface by molybdenum oxygen aluminum linkages and standing upright on the surface. Whereas type 2 under high sulfidation, severe sulfidation conditions would probably detect MOS slabs which are weakly interacting with the support surface. This then would suggest that leads to full interaction leads to high activity, and this in fact corresponds to the known fact that typically carbon-supported molybdenate catalysts are more active than aluminum-supported catalysts than sulfide under mild conditions. Now this observation can probably be explained and interpreted in terms of the electronic theory of Harris and Pianelli. They have come to the conclusion that the catalytic activity should be related to the metal-sulfur covalent bond pairing. Now it's clear when we do have very small slabs of MOS2 which are interacting with the support by molybdenum oxygen aluminum linkages, we would expect some polarization of these species decreasing the bond covalency, whereas after detaching them, weakening this interaction, we would have higher covalent bond character and hence higher activity. Now this would indicate that tailor-making a very active catalyst requires a very delicate balance between support interaction and slab size. On the one hand, we must remove support interaction, which on the other hand leads to growth of slab sizes and reduction of site density. Now at this point, I would like to turn to some considerations of the nature of coordination sites. Again, referring to the anisotropic reactivity of MOS2, we could certainly expect that coordination sites should be located along the edges of MOS2 slabs. For unpromoted materials, we can expect that coordinatingly unsaturated molybdenum sites are coordination sites, as we say, at this point. Now those coordinatingly unsaturated molybdenum sites can be present intrinsically on stoichiometric planes, or we can form molybdenum sites with sulfur vacancies in lower oxidation states by hydrogen reduction. Now, these type of coordination sites has been studied by hydration and spectroscopic techniques using probe molecules, particularly oxygen and nitric oxide. I do not have the time to go into details here. I only want to say a word this morning The second point which I want to make is the fact that, as usual, those site hydration, site characterization experiments are typically undertaken under conditions far from ideal. And this can lead to significant misinterpretation, particularly because surfaces may relapse. What I'm showing here is the surface unit cell for the 10 minus 10 plane, which has been suggested on the basis of electron microscopy as the most probable to be exposed. And you see that in this stoichiometric plane, there is one 4-coordinate and two 5-coordinate expressions. Now, this must not necessarily be the energetically most favorable situation when this surface is exposed to vacuum. It may rather relax into a situation which you find here with two sulfur atoms in non-balanced positions, now having two 5-coordinate molybdenums and one 6-coordinate. This is probably the situation which we would see when probing the surface of molecules, but there is no reason to believe that this is in fact the same situation as under the living conditions. Now, in the literature you find traditional suggestions for active sites of day. SH groups have been detected by titration techniques and also by neutron scattering experiments, and they were formed after hydrogen absorption. And it's believed that those SH groups may act in conjunction with coordinated unsaturated molecular sites in CS and CC hydrogenolysis reactions. In addition, it has been found by HTF that low valence state sulfur is present in the catalyst with minus 4 disulfide bridges. And good enough and people actually have suggested that disulfide bridges should exist along the edges of MOS2 slabs, and they have related groups to catalyst activity. It is in fact possible to detect those disulfide bridges by Raman spectroscopy, polycrystalline MOS2, and possibly also in sulfide catalysts to find bands at 530 numbers, which is characteristic of the SS vibration without disulfide bridges. Such disulfide bridges are very well known in organometallic compounds, for example, the MO3S13 anion, where you have 6 disulfide bridges and one single sulfur atom. And it is known that these disulfide bridges are in fact reactive towards dihydrogen. And this leads me to a few words regarding dihydrogen activation, which is surprisingly badly understood in this catalyst. Activation of dihydrogen can principally be considered to occur heterolytically on molybdenum sulfur pair sites to form molybdenum H and an SH bond. However, as just mentioned, disulfide bridges can also be reactive towards dihydrogen to form two SH chiral groups. Down here you see one well-established reaction for this molybdenum dimer being bridged by two disulfide bridges. They can react with dihydrogen, split the SS bond and form SH bridge SH bond. Now, which of these two possible activation steps of dihydrogen may occur or dominate is certainly not well understood. However, we definitely know that molybdenum disulfide, either unsupported or supported, can take up considerable amounts of hydrogen. This is expressed here as the stoichiometry HX-MOS2, with X plotted on the ordinate versus the hydrogen pressure for pressure ranges below atmosphere. Now you see that in temperature regimes typical for the catalytic reaction, we can easily reach values close to 0.05. When the catalyst is promoted, this hydrogen uptake seems to be supply chains. At this point, we may certainly question whether MOS2 is present under catalytic conditions at all. Rather, HX-MOS2 may be present under catalytic conditions, more so as the hydrogen uptake is further increasing and the pressure is not atmospheric. This view has very recently, I think for the first time, been emphasized by Anderson and Paul in one of their papers. Now, an important aspect of HCS catalysis, the promoted catalyst, certainly is the question of how the promoter actually works. I will not have time to go into detail, and I would only like to summarize three very controversial views which are still in the literature, and as far as I understand, still untold. Which one is first? The first view would be that cobalt and molybdenum coexist along the edges of MOS2 side slabs in interaction and to form new sites to increase intrinsic activity. The second view is that cobalt and nickel located along the edges of MOS2 slabs would increase electron density of molybdenum closer along the edges, and this intense electron density, particularly on sulfur, will certainly be favorable for dihydrogen accumulation. Finally, cobalt and nickel atoms are considered as the actual active sites, where MOS2 simply plays the role of secondary support for keeping cobalt and nickel atoms in high concurrence. Ladies and gentlemen, I hope I could demonstrate during last hour that our knowledge about the nature and genesis of this plastic catalyst has been largely increased over the last 2 decades. And this fact has motivated our chairman to state the optimistic view that we are pursuing. And certainly we should learn about the elementary set at a molecular level. I think these are areas where organometallic chemistry and theoretical chemistry have greatly assisted catalytic chemistry. Furthermore, the coordination of promoter atoms or the active atoms along the edges is still a matter of controversy. The role of molybdenum is purely acting molybdenum disulfide form as a secondary support, or it is interfering actively in the catalytic reaction as a result. And we badly need better techniques and methods for characterizing and titrating active sites. The nature of the food effect certainly is also not understood. And finally, I think an area which is not immediately related to hydroprocessing is the technological challenge, namely the development of HDN catalysts, which permit the hydrogenolysis of CN bonds prior to hydrogenation. Thank you for your attention.